Over the past few months, in fact for longer, a lot of people, particularly from non-technical backgrounds, have asked me questions like, what exactly are these cryptocurrencies? How does search engine optimization work in layman's terms? What is big data and what do we do with that? How does Hadoop work? Etc. While the technical answer to each one of these can be really technical, what I've realized is when we answer them by including technical jargons, it's not only hard for people from non-engineering background to understand, but also makes it actually more confusing. What I've also realized is that while these technologies are incredibly complex to implement, the core concept, the core idea under all of them is very simple. I mean, sometimes I wonder it's almost like we have done all of these things in our lives, like big data processing, cryptocurrency concept, growth hacking in terms of search engine optimization, monolithic versus microkernels, etc. Why didn't we then implement them and make a bit of money? So I decided to make this series of tutorial videos under the title Tech Like a Story. Technology like a story, where in each short video I attempt to explain tech that's either trending or widely in use already through analogous stories. While I will use technical jargons, I would do that only to explain the analogy. So for example, you wouldn't need any technical background to understand how big data processing works, or what exactly is a blockchain. All of it will be explained in the form of a story. Why? Because everyone loves a good story. And if a story has revolutionized an entire industry, it better be good. So today, we'll talk about big data processing, something that everyone seems to be doing today. Terms like HDFS, Hadoop, Spark, MapReduce are everywhere. Implementing a big data technology like Hadoop is an incredibly hard thing to do. But the core concept of what happens in MapReduce, which is at the heart of every big data technology, is actually a very simple concept. Something that can be understood in the form of a story. And it gets better. We all have probably done this in our lives, in one way or another. So today, we'll see how MapReduce works in the form of a story. We'll also briefly touch upon some core concepts of HDFS, which is the underlying file system, difference between Hadoop and Spark ecosystems, and a few other things. So, let's begin. The protagonist of our story is this student. We'll get to know more about his character soon, but for now, think of this grad student as the main character of our story. Like every story, there's a goal to this story as well, an objective. The storyline proceeds to see how our lead character achieves this objective. Now, what's the objective? Basically, he needs to submit an assignment the next morning, which is apparently a very important one, a game-changing one, a life-changing one. All hell will break loose if this is not accomplished. You know, there needs to be some dramatic factor. And the assignment is that there's this really big book that has 35 chapters spanned across 2,000 pages that needs to be quote unquote read and quote unquote summarized. That's basically it. The story is all about how he will do it. Remember, failure is not an option. Also, like any other story, our lead character has some drawbacks. Actually, they're not really drawbacks. He's just a normal dude, like any of us. He doesn't have a genius brain, so his reading and understanding capabilities are that of a regular human being. And he doesn't have a photographic memory, so he needs to write down things in order to revisit them. He's just any of us, not Sheldon Cooper. But, he's a rich student. Maybe that's where similarity ends between him and any of us. Being rich gives you a lot of amenities, like, iPhones, servants, a category of friends, TaskRabbit services, Thumbtack, and so on, depending on how rich you are. So he picks up his iPhone and starts calling his folks. Now, here's where I start comparing entities in the story with big data terminologies, or technical jargons that are analogous to things happening in this story. Our student can call up his friends and make them do his work. In this case, he's finding people on his own and, in a way, managing them. This is like having your own machines, basically commodity scale computers, in-house, and managing them yourself. Imagine our student didn't have friends who would suck up to him, or maybe he was an introvert. Maybe his friends were too unpredictable. In-house machines can be really unpredictable too. So he wants to find dedicated people to do his task. He manages to pay and find people on services like Craigslist, TaskRabbit, and Thumbtack. In this case, he has someone else managing people for him. He's just paying those services to get people to do his work, and when it's done, these workers go back to do other gigs for other people. This is kind of equivalent to getting machines from cloud services like AWS or Google Cloud. Less headache, but more expensive. Also, no hard feelings. Now the work starts. Oh, the story is gaining momentum. He assembles all of them around a table. Now, this looks like a trivial thing to say, but it is one of the most important things to be done. We'll see why in a while, but for now, just assume that this thing, called locality of reference, is a very crucial part of this whole big data thing. Although many research projects have attempted to disprove this, it's safe to say that this was one of the core foundations on which the big data processing was based upon. He then tears apart that big book into pieces. Well, not quite. What he does though is he splits the book of 2,000 pages into 40 parts of 50 pages each. Remember, the book had 35 chapters? This would mean that some parts might contain more than one chapter, and that some chapters might span across more than one part. But we don't really care about chapters at this point. We care about those 40 parts. These parts, which are of the same size, are called HDFS blocks. Basically, they are easier to act upon for the big data system because they are all of same size. In our case, these HDFS blocks are 40 pages in size. In real systems, these HDFS blocks are 64 MB in size, but it is configurable. Next, he does one of the smartest things to do. The 40 parts of the book we spoke about just now, our student takes each one of them and makes 2 additional copies of it. Why? Because for one thing, he's paranoid, which is good if you're dealing with a distributed system. He's afraid of one of his friends just leaving his place with the part of the book they were reading, or one of his friends just losing his copy somewhere. We don't want that. We need all the information intact after the whole book has been read and summarized. But equally importantly, our student also wants to make it easier for his friends to find the parts they are looking for quickly. If there are more copies, they can grab the one closest to them. Again, referring back to locality of reference. This is also what HDFS does. It makes 1 or more copies of all its blocks. Typically 2 or 3, but it is configurable. That's why it's extremely rare that you lose your data when stored on HDFS. In typical HDFS systems, it's called replication factor. Every block is replicated. Now the real work starts. He assigns each one of those parts to his friends and asks them to read and then note down the summary and the corresponding chapter number on a sheet of paper. Remember, the part number and the chapter number are different. A part is an equal-sized part of the book that's 40 pages big. A chapter is a usual chapter of the book. This is called the mapper phase in big data terminology. Note how the result of this stage results in each one of his friends writing down the chapter number and their summary on a sheet of paper themselves. We call this the key value output of the mapper phase. Note that each one of his friends is still writing down their individual summaries on a physical piece of paper. This is time consuming. If they had really good memory power, they could simply remember their summaries, and that would save a lot of time. This is an important distinction between Hadoop and Spark ecosystems, although there are many other differences. In Hadoop, the mappers write their outputs to disk, just like how his friends wrote down their individual summaries on a sheet of paper. But in Spark, the mappers just store the result in memory until they can't store anymore, at which point they start spilling it to disk. Think of it as his friends remembering as much as they can and only write the summaries down when they can't remember anymore. Anybody that's done reading and summarizing his or her part gets a new, unread part to read and summarize. This happens until all the 40 parts of the book have been read and summarized. When that happens, we say that the mapper phase has finished. Then starts a phase called the shuffle phase. Remember, in the mapper phase, we noted down the chapter number and their summaries. What essentially happens in this stage is that all the noted down summaries with the same chapter number come together. This is another place where, remember that locality of reference we discussed before, comes into picture. Imagine this. If all of his friends who were reading and summarizing were sitting in different cities or even countries, bringing all the summaries together would be a very time-consuming task. But luckily for us, we made them sit around a table. So it's easy to bring all summaries with the same chapter number together. We are now at the final stage of accomplishing our task. We're almost there. Now that we have brought individual summaries of a chapter together, all we need to do is to aggregate these summaries for each chapter. So who's going to do it? Well, the same friends who read and summarized the parts. Or it could as well be a different set of his friends. Or some from his original set of friends, some new, doesn't matter. What matters is that his friends now just aggregate the summaries for every chapter. This step is called the reducer step in big data terminology. Woohoo! He did it. He actually managed to read and summarize that big book. There are several important noteworthy things that happened here. Firstly, this whole activity took less time than just him reading the book and summarizing it. Way less time. Note that neither him nor any of his friends had any superhuman capability. They were all just like us, regular people. This is to say that big data processing is done using many commodity-grade machines rather than one or a few supercomputers. Also, hey, we didn't lose any part of the book. We still have all the information the book originally had. Now that's winning. Hey, but there's more advantages to the system. Imagine the book was 10,000 pages big, not 2,000. Or say we had 7 such books to finish, not just one. No worries. All the student needed was more friends, or more people from Craigslist. This is true of any big data processing system. Hadoop or Spark clusters used by giants like Google and Facebook generally have thousands of such machines, not just a few. Alright folks, we have now come to the end of the story. This turned out to be a happy ending story where our lead character, our student, accomplished what he wanted. Not everything works quite well like this though. For example, in our next story, we'll talk about the core concepts behind Bitcoin and blockchain, and what is Bitcoin mining. Until then, happy big data processing!